So in this video, we're going to be justifying that why do we define matrix multiplication in this particular fashion. I mean, why not something simpler? Why not something like matrix addition? You know, we could have defined matrix multiplication component-wise, but why did we choose this particular definition? So we're going to get into that, and before actually going to understand that what matrix multiplication is, let's just take 2-3 minutes to understand that what exactly a matrix is. Because generally we think of matrices as two-dimensional arrays that are used to store data and information, and that is so not the case. So we're going to see that what a matrix is, what is it representing, is there any geometry behind it, you know, we're going to cover all of that. So to begin with, I'm simply going to define a function. So let us name the function t, and the domain of the function is going to be the xy plane, so r square, and the codomain is also going to be r square. And I'm saying that this function is going to take the point or the vector xy, and it is going to double its size without changing its direction at all. So I want you to imagine this guy. What is it doing to this space? If I had this vector, it is going to stretch it out by a factor of 2. If I had this vector, it is going to stretch it out by a factor of 2 in the same direction, right? If I had this vector, it is going to stretch it out by a factor of 2 in the same direction. So essentially, what it's doing to the xy plane is that it is going to elongate, it is going to stretch the xy plane by a factor of 2. So you can also think of this as a transformation because it is transforming its domain space, right? So this here is a transformation of the xy plane. You're just stretching every single point, every single vector by a factor of 2. So this here is what we call a transformation. All right, and I want to investigate that where is this transformation going to take the vector I cap and j cap to, right? These are the most important vectors that we have in our xy plane. So I'm going to simply track that where are these vectors going to go. So this is I hat and this is j hat, right? So when I apply the transformation t to I cap, I will notice that t of 1, 0 will simply be 2.1, 2.0, and this is going to be 2, 0, right? We're going to elongate it by a factor of 2. So the landing point is going to be over here. This is 2I cap, okay? Similarly, if I wanted to investigate where j cap is going to go after the transformation, it is going to land on 2j cap, and the coordinates for that are going to be 0 and 2. And if I stack these two vectors, one in front of the other, okay, side by side, I'm going to stack them, I will get a matrix, right? So what's happening here? I'm going to recapitulate here. This guy, this column vector is the image of I cap under t, and this column vector is the image of j cap under t, right? Write them together, you get a matrix, right? So this is what essentially any and every matrix is doing. Every time you see a matrix, you should think of this thing. Okay, the first column is going to be the image of some function of I cap. The second column is going to be the image of the vector j cap under some function. Let's take another example to illustrate this. So this time what I'm going to do is I'm going to first give you, I'm not even going to write what is the function, okay? I'll simply tell you what it's going to do geometrically, and we will figure out that what the corresponding matrix is. So imagine the xy plane, and I want you to visualize that what would happen if I were to rotate this xy plane by 90 degrees in the anti-clockwise direction, right? Where are the vectors I cap going to land? Where is the vector j cap going to land? Okay. So this guy is I cap. I'm sorry for the drawing. In fact, let me just draw it properly. So this guy is I cap. And when I rotate the plane by 90 degrees counterclockwise, the transformed I cap is going to be over here. This is going to be d I cap. So the coordinates, the new coordinates of I cap are simply 0, 1, x coordinate 0, y coordinate 1. What would happen to j cap? Well, this over here is j cap. I'm going to rotate it by 90 degrees. J cap's new landing is going to be this guy, and the coordinates are -1, 0, x coordinate -1, y coordinate 0. And there you go, you found your matrix. the matrix corresponding to this transformation is simply the first column is going to be the image of I cap, so that's 0, x coordinate 0, y coordinate 1, and the second column is going to be x coordinate negative 1, y coordinate 0. And what this transformation represents is a 90-degree rotation of the space in the counterclockwise direction. And that's it. That's what matrices are. They're essentially just transformations of the space. So now we have some idea about what matrices are and what do they geometrically represent. There are certain visuals going on behind matrices, and you can create a bunch of matrices like that. You can sort of imagine transformations of the space and you can write corresponding matrices to them. Now we have to get to matrix multiplication, and we're going to use these two matrices as examples to illustrate that why matrix multiplication is defined the way it is. So what I'm going to do, I'm going to call this guy T1, which is responsible for stretching the space by a factor of 2, and I'm going to call this guy T2, which is responsible for rotating the space by 90 degrees counterclockwise. And I want to compute what is the matrix product of T1 and T2. Okay, now what this strictly means in visual terms is that first apply T2, whatever resultant plane that you get, apply T1 on that, and that is it. That is what matrix multiplication is. So every time you see two matrices multiplied together with each other, what's really happening is that you first apply the right transformation, then you apply the transformation on the left. As simple as that. So without using the formula, we're going to actually write what the matrix product is going to be. So essentially what we'll be doing is, let's just write these two matrices side by side. So we have 2, 0, 0, 2, we have 0, 1, negative 1, 0, and we want to figure out what the resultant matrix is going to be. So basically I just have to figure out where I hat is going to land after applying both of these transformations and where j hat is going to land after applying both of these transformations, and I'm done. Because I know that in order to figure out what the column of this resultant matrix is, I need to track where I hat is going. So the first thing I do, I see that where this transformation I hat, where is this transformation going to take I hat to? So I know by definition that the very first column is going to be the landing position of I hat via the second matrix, right? So now I am left with the question that where is this transformation going to take this vector to? So all I have to ask is, I'm going to plot this. So x coordinate 0, y coordinate 1, and I know what this transformation does geometrically. It just elongates the vector by a factor of 2 without changing its direction. So I know it is just going to stretch this vector by a factor of 2, and the coordinates are going to be 0, 2. And this is the final destination of I hat after applying both of these transformations, and I have got the first column of my resultant matrix. Similarly, I can compute the second column of my resultant matrix, and I highly encourage you to pause the video right now and try to match with me later. So if I'm going to track what is the journey of j cap in this entire process. So I know that the second column of this matrix is going to be the result of j cap after this transformation. So I'm going to draw it again over here. So negative 1 and 0, this is negative 1 and 0, and now I want to visualize that what is going to happen to this vector after I apply this transformation, right? I know that it is going to get stretched by a factor of 2, so the new coordinates are simply going to be negative 2, 0, and I'm going to write it in that fashion. X coordinate negative 2, y coordinate 0, and this is really the matrix product. And I would really appreciate if you could just verify it by the rule that I have written in the top of this document. Here is the actual rule that you would find in any standard textbook of matrix multiplication, and if we simply just try to verify our geometric intuitions via this rule, it would really match, right? So 2 times 0 is 0, 0 times 1 is 0, you're adding 0 and 0 and you get this guy. Similarly, 2 times negative 1 is negative 2, 0 times 0 is 0, add negative 2 and 0, you get negative 2. And similarly, the second row will hold as well. So you can see that what really is happening. So basically, we've got two matrices, and in order to define what matrix multiplication is, we just have to apply two transformations one after the other, And what does that mean mathematically? We're just composing two functions. Transformations are just functions, and applying them one after the other, trying to track that where is I cap going after one transformation and where it is going after the other transformation is just a fancy word for composition, right? That's exactly what we're doing. So now we're going to prove why we define matrix multiplication the way we do in the most general case, that is the very first line of this document, and we're going to simply crack the entire formula. So we have A, B, C, D, E, F, G, H, and we want to know that what are the entries going to be here, and that's very simple. I just have to track that where is I hat going to land after the end of this transformation and after the end of this transformation. Well, I know by the definition that I hat is going to land at this vector, EG, right? So the next question that I have is, where will this transformation or where will this matrix take the vector EG2, right? This is basically all that I have to find. And well, what I can do here is I can write E and G in a clever way, that is, I can write EG in terms of I cap and J cap and simply figure out where this transformation is going to take this vector to, right? So EG can be written as E times 1 0 plus G times 0 1, which is E I cap plus G J cap, right? And I'm going to name this matrix, let's say T2, right? So now I have to figure out what is T2 times E I cap plus G J cap. Now there's a rule that these transformations follow. They distribute over sums, right? So this guy is equivalent to this guy, and every time there is a scalar that is multiplied to a vector, you can take out the scalar. So you have E times T2 I cap plus G times T2 J cap, right? And we know what is T2 I cap. We know we can just look at the matrix. The first column is going to be the image of the vector I cap, right? So what is the first column of this matrix? It's AC. If I want to know that where is J hat going to land after the transformation T2, I just have to look at the second column of this matrix, and that is BD, and I'm just going to multiply them in the ordinary sense. So this is a scalar and this is a vector, so I have to multiply it with each component. So EA, EC, and here I have GB, GD, isn't it? And I just multiply them component wise. These are two vectors, so EC plus GD, and this is the entire journey of the vector I cap after the end of these two transformations, and this is my first column of the product matrix, right? So I should go ahead and write this over here. So we have EA plus BG, and in the second column we have EC plus DG, right? And similarly we can track where is J cap going to go, and that would help us determine what the second column of this matrix is going to be. And I highly encourage you to pause the video and try that on your own. So I'm just going to do that for you. So again, let me just write these guys down. So we have A, B, C, D, E, F, G, and H, and I'm interested in the journey of J cap. Well, I know that this transformation is going to take J cap to this vector FH. So the only thing I have to figure out, where is T2 going to take FH, and by the very same rules I have T2 Fi cap plus Hj cap, which is equals to F times T2 I cap plus H times T2 J cap. And I know what is T2 I cap by this matrix. Well, it is F times the vector AC and H times the vector BD, right? And I'm just going to write it in its final format. It's going to be AF plus BH, multiply F with C, and we have H with D, and that's the second column of my final matrix. So we have AF plus BH, and CF plus BD.